Howdy, 216ers. This is Professor Kaufman, and what follows is an overview of your Project 4. This project is a recreation of what the basic functionality of a makefile is like, and in honor of that, we're calling it Bake. As you might have surmised, this overview video is happening somewhat midway through the project release. And unlike previous projects, this went out in parts. That there was a first phase release that released the first couple problems, second phase that went out last night that entails problems 3 and 4 and test cases associated with those. It's likely that there's still some bugs around, and so as you would want to update any files that you have around associated with the project, issue this little incantation, which will download a script and run it through bash to additionally get any project files that need updating, like test files and so forth, as well as making backup copies of what you have around just in case you need it. So I'll walk through on the presumption that you're maybe just getting started and want an overview, but as usual, I'll touch on all parts of the project, both early and late, and do a little bit of setup for those who need a hand getting worked up there. I'd encourage you to read something about the sort of overview at each page, but it's totally fine to sort of take this in piece by piece. It's one big project, but the subdivision then can feel a little bit I'm just scattered, I'd say. It's like, okay, there's work on this piece here, then work on this piece here, once they work on this piece here. And seeing an overall sort of flow of how these things fit together is maybe something that you'd want to do some reading to do, or some thinking for that matter. But this kind of endeavor at this stage in your CS career is meant to sort of teach you about it takes some work to sort of design something, and you should look forward to doing that as you go forwards, and maybe take some lessons from this about things you didn't like about this design. But generally, I tend to think about things sort of top down, that these things need to happen, and that dictates then breaking it into pieces, individual functions, and then thinking a little bit about how they'd fit together before actually going on coding. You'll be working on it probably from the bottom up, as problems 1, 2, and 3 largely deal with utility functions, not utility functions, but service functions, we'll call them, that have to fit together to manipulate the parts of this. And then that's all tied together in the last problem that has you make use of a main function that will sort of call some of these functions in sequence. Generally, there are just two files you're going to edit, bakefuncs.c and bakemain.c. This will be all the service functions, and then problem 4 deals with writing the main to tie all that together. Each of the problems has test cases associated with them. Those test cases are spread across 1, 2, 3, and 4 sort of scripts, along with some C files that support that. And in the first release, we just had these first couple, and the second release phase there. I should mention at this stage there will be one more phase to this where we'll release some makeup credit problems that augments a few extra functions for some goodies there, for those who want to make up credit on this future or past projects where they've lost credit. So the idea of the bake system is to replicate a simplified make. And so if you've not done a past lab that studied the essence of what goes into a makefile, I'd encourage you to revisit that. Generally, you'd see a structure that looks sort of like the following, that comments lead with hashes, just as they would in like a Python or shell script here. But otherwise, the arrangement is that of rules. And a rule is comprised of a target along with dependencies, and then some commands that are run in the event that the make or bake system detects that this target needs to be updated. That might be because it itself is sort of out of sync, or that some of its dependencies are out of sync, that they need updates. If you've not spent some time to sort of understand that structure and the data structure, it's tree-like. It's actually a directed acyclic graph here. That this demo depends on hello and bye. Hello depends on a .o file, and hello.o depends on a .c file. Then I encourage you go back and look through that to get a sense of it, because it would be otherwise hard to understand if you don't have that in hand. Now, Bake being a simplified version, certain conventions will be at stake that this is interpretable by Make, but the opposite is not true. It's Bakefiles are sort of subsets of what Makefiles look like. There are no variables in here. Certain spacing conventions, like you always have to separate out the target and dependencies over here with a space colon over here. And the fact that comments only can begin at the beginning of line rather than anywhere with hashes there. But most of that stuff is sort of inane, and thankfully for all of you, the parsing of this file to create an initial data structure out of it, that's handled by my own code that comes out of this bakeutil.c function. And so you don't have to worry about that parsing exercise. It's very interesting, and if you have a look at that code, it'll prepare you perhaps for later things like CMSC 30 where you have to do some parsing and so forth. But generally parsing in C is a huge pain in the ass, and a lot of the conventions here that are simplified are to make the parsing somewhat more palatable and less error prone there. So the central data structures then are on parsing this file, a bake t struct will be created. Now, baketees basically reflect the structure of the file itself. So its central feature is an array of rules. So there'll be a rule for demo, a rule for all, a rule for hello, a rule for hello.o, etc. The rules themselves then have several features like what is the target, by.o, what are the dependencies, in this case just a single .c file. In the case of clean, as a rule, it has no dependencies, so that'll be empty. But in the case of demo, it would have a couple entries in an array over there for that. And then finally, rules have an array of commands as well to execute. Demo up here has 4 of them, whereas all has none, and hello here has 2 out there. And that is encoded in a command T struct that has a few extra features associated with it. For instance, commands could just be sort of normal. We'll also support silencing of commands with proceeding with this little @ here, so that'll demarcate this individual rule. Echo running programs is don't print the rule as you run it, just do the rule, and that's oftentimes associated output over here. But we'll also have I/O redirection, as in, the results of printing could go into a file, or this command could read in some inputs, and that'll give you a chance to make use of some of those I/O redirection things that you've been studying. So this design is, somewhat, I don't know, it's chosen for convenience and to enable ruling. There's a lot of things that one might criticize about it. But it has the following things that are worthy of note. So the baked, and we'll look at the header file for this in just a second. The baked has an array of rules, and this is malloc. That means it can grow, and that eases up parsing so that as I'm reading through this file, I can say add a rule for this, add a rule for this, add a rule for this. The other parts of it, though, for instance, within a rule, there's an array of dependencies that we'll see in a second, and an array of commands that we'll see in a second. Those are a fixed length. And this limits it somewhat so that there's like 128 dependencies you could possibly have over here and 128 commands over here. But it doesn't make a lot easier that an individual rule is a fixed block of memory. So it doesn't require much there. And that eases things like, you can allocate an array of it and don't have to worry about chasing pointers or mallocing things further underneath. It does limit it then in terms of the maximum amount of stuff that can appear in a command, or the maximum number of commands, or the maximum number of dependencies, stuff like that, which is, maybe not something you'd want in a production system, but is good enough for our purposes here. So we'll follow this up down here with a discussion of the service functions, and we'll start going through some of those in just a second. But I think a good idea at this point, because we're very shortly going to go on to make use of this outline, is to get the project code in place. That'll allow us to have a look at the header file. This bake.h is provided, which outlines each of these data structures, structs, and then we can start doing some copying and pasting of the outline here and get online in terms of getting the first set of tests to run there. So let me just buzz back up to the top up here, and I'm going to grab the project file. I'll copy that link address over here. I'll flip over to my Emacs instance, which provides a shell and then some editing over here, and issue the standard sort of wget to plop down that project code. And I'll unzip the p4 code.zip that's provided there. That'll create a bunch of stuff. Refresh this directory. I've now got a p4 code over here. I might just out of safety delete this one so that I don't inadvertently submit the empty project submission. And then over here, I'm downloading this now when we're sort of past the sort of first phase release and into the second. So I have all of the test files, these test bake funcs for 1, 2, and problems 3 and 4, along with supporting files for that stuff. And also then some updates and other files that are there. But you'll notice in absence of the files that I'm supposed to create, this down here, the bakefuncs.c and bakemain.c, which is up to you to create there. Now, we just got onto that subject of these bakefuncs.c. This outline, as has been provided in the past, is useful as a starting point as you'd want to create that file. Let me start up here. I'll just highlight a little bit, and we're going to grab the entirety of this thing to make it easy to plop down a version of that. So I'm going to use the convention Emacs to create a new file. I'll call this bakefuncs.c down here, and your editor of choices might be to create a new file, like punching a button or pressing Command N or something like that. Emacs is a little esoteric in that way, but now that I've got this bakefuncs.c set up over here, I'll yank out all this text. And now I've got my outline for this here. Importantly, if I look over at the project directory again, most of these functions are going to need to make use of other functions that are around. For instance, the provided bakeutil.c has a bunch of stuff in it that I will maybe eventually need. So I can lift the following. Oh, there's a include of bake.h. We'll look at that in just a second. So I should probably bring that in over here as well. That'll make sure as well to bring in as we look at it, and I may as well pull it up now, certain headers like, good old stdio and stdlib for malloc and printf and so forth, as well as a bunch of the Unix system header files that will allow for exec and wait and other things like that we've been talking about, system calls, to be made use of in here. Okay, so with that set properly here, I want to take a quick tour of this header file so that you are aware of a few things that are in it. Let me skip down just a little bit here, because we'll talk about some of these other things, because I want to draw attention first to those data structures that are of import. We'll go in reverse order because this is a sort of top-down. A bake t struct, again, is comprised primarily of just an array of rules, and those would come straight out of the file. So the example file is provided in the project specification that was up here. It has 1, 2, 3, 4, 5, 6, 7 rules in it, one for each of these targets that's mentioned. And so in looking at this thing, I'd expect that this malloc array would be big enough to hold 7 things, and this rule count, that would be 7 in the case of that example file. Well, since it's malloc and it has this sort of expandable array quality to it, we'll see this later, you'll also track a capacity, as in what's the maximum number I could presently fit in this rules array. And this will be progressively higher powers of 2, like 4, 8, 16, 32, etc. And part of one of the problems that you implement is to add new rules and expand that array using realloc if needed here. We'll get to that in a minute. A few other ancillary things are of interest. The Bakefile or the Bake tracks what file it came from, as well as sets up something called a string table. So there's a bunch of need for strings, like the target string and the dependency strings over here. This will be one big block of memory that has all those strings in it, and pointers here will point into that. Makes it somewhat simpler to deallocate, because to get rid of all the strings that everything's pointing to, just get rid of this one thing. Again, that's handled in parsing, so you don't have to worry about too much, but if you're curious about design elements, you may poke around that a little bit more. It's not an uncommon kind of feature to see in things, for instance, ELF file formats, which are the executable file format of all the programs that we write. They make use of similar techniques there. All right, so looking backwards just for a second, here is the rule struct. And so this array of rules over here is comprised of structs of this kind over here. They have a bunch of parts to them. For instance, during parsing, it's tracked what line number did this rule come from. And looking back here, say like, the rule for hello came from line 17 over here. That makes it easier if something goes wrong with this rule that you can report what line number it is on. Maybe someone misspelled a command or something like that. It has a target, so in that case it'd be like hello.o, something like that. A bunch of dependencies, and so this would come from the dependencies over here, hello and bye for the target demo, hello.o for hello, etc. Sometimes empty over there. There's no need in this case to track the number with a count or anything like that, because after the last dependency, just plop down a null. This makes it possible then just go in sequence printing out dependencies or visiting dependencies, and when you hit a null, then you're done. And then there's an array of commands associated with it, along with a count here. Commands are a little bit trickier to use because they're not pointers. These are the actual command structs that are in here, no stars about it. So we'll keep a count there. But again, that's set up during parsing. The final thing is that there's some qualities to rules that are tracked. And these are listed on here. This follows a typical systems convention that these are a bunch of true falses, and so we'll put them essentially in a sort of bit set. That bit 0 is an on-off flag that means, yes, this rule needs to run its commands because the target needs to be updated, or a 0, no, it doesn't. And that's encoded down here with a rule bit update, or rule update bit. It's the rightmost bit there. Second rightmost for the implicit bit, a certain kind of rule that we'll talk about briefly, that's set up. And then this visited bit, which isn't used in the standard project, but is likely to be used later on in some of the makeup credit to detect cyclic dependencies. More on that a little bit later. So to manipulate these bit fields, and there's one for rules as well as some flags associated with commands over here. There's these pound-defined constants that sort of are amassed to say I can change this bit at this spot or at this spot or this spot without affecting others. There's also some convenience macros that are up here that look sort of like functions. So set a bit, clear a bit, or check a bit, return a true false, truthy falsy value, but to see if it's there. So I'd encourage everyone to make use of these. They just encode in a somewhat simplified fashion some of the bitwise operations that we've talked about with ors and ands down here to fish out individual values. I'll try to point that out again as we go through the project. So then rules have several things, one of which is an array of commands, and the commands is up here. Commands are comprised of a bunch of tokens, and this is then a sort of space-delimited affair that's on the command line. So, for instance, the tokens associated with this hello.o rule over here, its first command, only command here, reads GCC, so that'd be the 0th token, -c, the 1th token, and hello.c, the 2th token, followed by a null again to indicate the end of that. Rather than store the whole string here, that tokenized version is just a little bit easier sort of during parsing. And as well, the idea eventually is to take this thing and exec it, to launch a child process which execs takes on the identity of GCC. The convention associated with those exec family system calls is often handed an array of strings that are comprised the 0th, 1th, 2th, 3th argv that's me on the command line. So the fact that these are already tokenized for you makes that just a little bit easier. In addition, there'll be input and output direction possible. So this will be with the greater than less than signs, and flags indicate whether or not the command has been silenced. Don't have any indication of input-output redirection in this particular file, but the silencing with the @ up here, that's something that you'll have to set the bit for eventually more towards the end of the project. Okay, so as a quick tour of sort of data structures to expect, various of the functions then that you'll implement will work with these data structures in different ways. Okay, so let me come back then to the funcs. And we may as well sort of talk through the first bit of business here in the project. And we'll go problem by problem here. I'm going to skip over this stuff out here and sample uses, and we'll just sort of fast forward to problem 1. If you are curious to get a sort of overarching view, you may want to look at some of these usages over here. But let's just start, as most folks will, or just sort of barreling into the code here. The function that I wrote to parse the Bakefile intentionally relies on a little bit of code that you all are going to write. The first is to slurp in the entirety of a file so that it's an in-memory string, just a malloc array of characters there, as that's useful then in the parsing rather than going line by line. It's possible to do so, but this is a good opportunity for all of you to revisit this idea of reading a file in its entirety efficiently. This isn't always a good idea, particularly if it's a gigabyte-sized file, as it would occupy a lot of memory. However, for smallish files like this, can be a tremendously convenient way to do things. And the slurping here can make use of the stat and the read system calls that we've studied in order to make the reading relatively efficient. And you recall the stat system call, which is designed to give you statistics about a file, one of which is how big it is. And so this slurp efficient, file efficient function can boil down to just a few sort of lines of code that will stat the given file name to figure out how many bytes big it is, and then open it up and use read to slurp in. A single read call is often sufficient for modest-sized files to read things in. Now, we're not going to sort of go into the exact details of that because that's part of fun of writing it, but it's not hard, and would encourage everyone to sort of poke around some of the examples we've seen in lecture about that. One caveat here, it is possible that on trying to read all of the bytes of the file, you don't get all of them in the first read. We're not going to worry about that too much. Sort of properly written version of this might iterate several times on read to make sure that you get all the file, but the small files will deal with it. It almost always works, so don't sweat that too much. So this might be as simple as so like stat, open, and read with a little bit of error checking for each to make sure it's there. We may as well fill in just a little dummy version of this thing in the code so we can start to get things up. And this will be a good chance as well. The tests for the first couple problems rely upon certain functions having definitions to them. And so, as is often the case over here, all we have is an outline. So I can fill in a sort of dummy body here just by returning null in this case. And may as well sort of go through and do appropriate things for each of these as well. So this would be here, it wants a pointer back to a rule, so I'll return null. And as well here, a pointer again to a rule, I'll return null is good enough. We have to do these for all of the problem 1 and problem 2 functions, so this may take just a minute here. Maybe I'll just return -1 here. I'm not sure. I haven't read that one and can't remember right now what it is. That's a void, so that's easy enough. Don't need any return, and we're already on to problem 2 stuff here. Let's see, I think that's the only one needed for this. And this one is, I'll just return -1 for an error for problem. Okay. Now, if I remember right, the tests for problems 1 and 2, that's all they'll need. So problems 3 and 4 down here, we can leave off on that for the moment. And to that end, let me pull up quick a shell, and I want to first get into the P4 code, and then try make test prob 1 to see if we over there. Hey, compiled. All right. Oh, that's pretty good for the first time. Now over here you can see this is all like failures, but that's more or less expected. Oh, I even got one right there that it's an okay for this, but I think it's because I'm returning a null, and the expectation is like a null there. So we'll worry about like a passing and failing later on as we actually sort of go on to these. You can see first 4 tests here or so, they deal with this slurp file efficient business, and so we'd want to start filling in bodies to that thing. Yeah, okay. So I'll leave this one to you. It's not particularly hard to do. The next couple functions, they deal with adding and manipulating the Bake-T rules array. So the descriptions here are essentially take this Bake-T and find the rule that's associated with this target name. And that is as easy, in most cases, as traversing an array. Down here, the rule T, it has this... Or sorry, the Bake-T, it has this array of rules, so you're just iterating through that array, and each rule has a target, this thing. So you'd want to say, hey, this string that I've been given here, target name, is it equal to this target over here? Bear in mind, this is supposed to be a deep comparison, a string comparison, so you'd want to make use of a function like strcomp for that. Equals will not cut it in those cases. I helped a few students with that part. And if you don't happen to find the named rule in there in the array, then you bail out. But once you do, then return a pointer to that element of the array there. So keep in mind then that this rules array here, It's a pointer to a rules array, but each element of it is an actual rule. So you can't just return the contents. You'll rather have to return the address of that contents because a pointer to that spot in memory is what's desired there. This will revisit a bunch of the things that we've talked about in C in terms of passing back addresses of things or making use of certain functions for comparisons. This will revisit that and hone your skills a little bit in a somewhat more complex scenario here. The bake add empty rule then is needed by the parsing code as well. So we need several of these functions to sort of work through. But bake add empty rule is what my parsing function is going to call to say, I need space for a new rule because I'm reading it in, so give me space, and I'll start filling things in there. Now, this is interesting as it presumes like, okay, here's this rules array, and if there's space, then just return the next element in it. So let's see if I find here, I've got the count of rules, and if it's 0, then my capacity is something like 4, which would be by default. Then the 0th element of this rules array is available for use. A little bit of nuance there. You want to return a pointer to this thing, but you'll also want to initialize it to be completely zeros. So rules have all these parts to them. They have got a target and a depths and an array of commands and so forth, a count and a rule flags and so forth. All that stuff should be set to 0. And as well then, if you've got an array of depths, you'll need to iterate through and nullify each element of that as pointers, and visit each of these commands and nullify all the parts of that, like all these tokens array pointers and the pointers that are in here. That can seem like a lot. As in it would be sort of recursively visit every part of this thing, and it could be 50, 60 lines of code to sort of get through that with a bunch of loops and so forth. Or you can acknowledge the fact that by virtue of this design, that a rule is actually just a rule, and therefore everything in this struct here is like, oh, the struct actually contains the entire array of commands, and everything in here is like in there. So setting it 0 is just set this entire block of memory associated with the rule to be zeros. There's a very well used function for that, and I think it's mentioned in here, the memset function. This has semantics that are similar to lots of other low-level memory manipulation functions. It says, you give me a pointer, and you tell me how much space this thing points at, and I will set it to a constant byte, oftentimes a 0. So there's 3 parameters, a pointer, a byte to set it to, usually 0, and a size. And that's all that's needed then to set the entirety of an empty rule to be all zeros out there. This is required because the block of memory that comprises the rules array is uninitialized. It's allocated via malloc. And to that end, it will not have good stuff in it. Memsep's an easy way to get well-defined zeros in it there. Now, the other part of this is a little bit nuanced. Again, this rules array, it's one that is expandable. So as I visit and find, hey, I've seen 4 rules, but I need to add a 5th one. This array is to be expanded, and it is the job of the add empty rule function to do that expansion. So upon seeing that someone wants to add a rule, but the count is 4, the capacity is 4, the objective of this function is then to expand the array. The realloc function is extremely useful for this. Without it, you'd be obligated to do the following. Malloc a new block of memory that is twice as big as the current array. And that's not, it's 4 elements, so I need to allocate elements. It's, 4 elements times the size of a rule, which is substantial. And so you'd want 8 elements times the size of a rule. So you'd malloc this new thing, then copy over all of the elements that are present in it, the older version to the new, bigger version, and then deallocate the old version and return a pointer to the new version. All that's actually handled by realloc. The find me a new memory area that's yay big, copy over the old elements to that new area, and then deallocate the old one. You'll want to do a little bit of reading about the proper use of realloc, but it has very malloc-like semantics. It's like, here's my old pointer, here, but aside from that, it's like, what do I want the new size to be over there? And it's handy to know about for these cases. When we make use, or sort of in our last project, we'll probably revisit this just a little bit to talk about, in some cases, Realloc doesn't actually need to find a new memory area. That due to the heap layout, it can say, oh, I can actually just expand the current block of memory a little bit, which is more efficient. But in the worst case, it's just sort of find a new block that's bigger, then copy things over. And I encourage use. In fact, it's a project constraint to make use of this so that you become aware of it and then are able to use it effectively later on. Prepare the way for future projects. But generally, both of these functions are relatively short. The one involves like a short loop over the rules array. This one involves just a few conditions and a few uses of like realloc and memset there. So shouldn't break anyone's brain too much. And this will get you acquainted with some of the structural elements of like what the Bake and the rules about look like there. In my initial release, I didn't mention that, using memset is a good idea there. I just assume folks would know about it, but that's a really bad assumption that, as you get older and more experienced, you just, assume folks know about things. But education is about making those assumptions explicit. And so here they are now. And so you can add a new function to your repertoire there. The next part then of the first problem is to do a little bit more structural manipulation of the bake T struct. So oftentimes, as I'd want to specify something like a makefile or the simplified Bakefile here, you'd want to specify things in the following way: that I've got a program A and it's got a source 1 and a source 2 that's dependent on. Source 1 is dependent on a source file, like a .c file, and I'd convert it to a .o by issuing some GCCs, and similarly so for source 2 over here. What's not mentioned is that, there's sort of a presumption that source1.c actually exists and is a file there. So these three explicit rules, in order to make our job easier in terms of processing, the structure of this, will actually add some so-called implicit rules to say that this, as a dependency, will make it explicit. In the bake T struct, like add in source.c, but that's there. And it has no dependencies, has no actions to be made. It's there solely to say, like, okay, before I could actually do this source.o business and GCC it, I have to make sure that this file exists, like is on disk someplace. Because if there's no source.c, there's really no point going forwards at this stage. And so this will convert then all the explicit stuff and just augment it a little bit, decorate that structure, the bake T, with some additional implicit rules there. So as you would take and get the initial parsing, the bake T would sort of reflect this structure. And then this function you're to write, which is add implicit rules, would go through each of the rules and say, hey, if this source.o thing, it exists at explicit target, and it does, there's nothing to do. However, if this dependency, source.c, exists or doesn't exist, then I'm going to add it and set the implicit rule bit on it to indicate that, okay, it's now in the bake T struct, and now I can sort of handle it specially later on. This will help in recursion in that, like, you won't ever get into a situation where, like, hey, I want to go visit this thing, but there's no target that's, named source.c, and so this might break the recursion. Now there will be, and so the processing of that can be just a little bit more regular than the later functions. This will again give you a chance to exercise a little bit, modifications of this bake T, calls to your very own add empty rule function. And for this one to work, you'll have to have that in hand, as well as then make use of those macros to manipulate the flags, in this case, the implicit bit for the rule, to say, this is not a normal rule, I added it in as an afterthought to make the data structure a little bit more regular. Finally, the first problem ends with visiting the other major struct, this command T struct. As this would be parsed in, you'd have something along the following lines, that there'd be like a tokens array, and this is part of the command T. It'd be something like GCC is the 0th token, -o is the 1th token, program is the next token. It appears much more sanely up here, but this would be the C struct equivalent to that over here. Oh, and I can see I have a little typo there, but double the double quotes, so it's a quadruple quotes. I'll eliminate that to get the syntax high a little bit better. So the idea of bake print command is just to familiarize yourself with some parts of this. Is this would be printed out, you'd want to print out this thing all in one line. However, there are a couple caveats to that. in some cases, commands will be silenced. And we saw up here in the sample Bakefile, if I come up here, Bakefiles, the little @ here means don't print this thing. And so as you would sort of see that bit set in the equivalent struct, and I'll have to try and find right here, there'll be a baked a silence bit. And let me show you where that is in the struct here. So the command T has these flags. The 0th bit is silenced, and so silences don't actually print it. So there's a way to check, like, oh, the command silence bit, use that with like check bit over here or here. And basically, that's the easiest case. Like, oh, if that bit is set, like, don't do anything here. Otherwise, iterate through these tokens and print them out, as well as augment this a little bit with if there's an input and output redirection, do some printing there. So the command T has some bits that indicates input and output redirection. They also have some pointers to say if I want to read files, read from a file in this command, then this will be set to the string. That is the file name for that. And output redirection, similarly, if I'm going to print into this file, or output should be redirected in there, but then this will be set to a string that's associated with that. So to that end, print things out after checking those things. So it's just like a little loop along with some special cases to sort of print out if those two things there with a little shell input redirection, output redirection symbols there. Okay, I don't have any examples of that, but I should. And let me just flip up here to the sample usage because I'm pretty sure some of the Bakefiles, oh crap, I don't have anything in here. Okay, never mind. I should have. Oh no. Okay, it's a simple Bakefile. I'm just looking for one that has the input-output redirection in it. I don't have one here. So I mean, there are a bunch of them in the sort of demo files I provided, but I'm sure you're all acquainted at this point by some of that stuff. If not, it'll come up later in the conversation. Okay, so problem 2 deals then with just a single function, but it's somewhat complex and is the spot where you'll make use of the most system calls. This bake execute command, again, deals just with a command T struct, like the printing command was, but it's actually responsible for forking and execing that command. So on completion of, on arriving at a command, and I really need like a second browser window for this here. So let me grab this thing and open up another tab here so I can go back up to this Bakefiles up here. On running sort of a bake here, you might get to a spot where it's like, oh, I need to build this hello.o here and issue this command. The idea of then performing an update like that is to fork a child process, which will also start out looking just like the normal bake process, and then exec in that child process this gcc-c hello.c. Now this is made fairly easy by the fact that command T, it just has this tokens array. And if you're going to call a standard like exec vp, they'd be like, oh, what's the command you want to run and what's the argv array there? The command I want to run is here in the 0th element of this tokens array. And the argv that I want to pass as the second thing to exec vp is like this tokens over here. If you need examples of that, buzz over to numerous lecture examples that we dealt with, as well as some lab examples from last week. And those will definitely set the stage for how to exec a child. Hopefully at this stage you've also sort of talked through a little bit about, oh, when I fork, then I'll have an if-else for parent-child, and as well some separate code that the parent will handle there. Now there are some caveats here. For instance, as the child execs, it will first want to set up any I/O redirection. So if some fields of this are set, for instance, the input redirect is set and this little pointer is non-null, then you'll need in the child process, before you exec anything, do a little bit of dupe toing. Let's say, rather than read from keyboard inputs, this child is supposed to read from this input file that's going to come in. Or alternatively, rather than print the standard output to the screen, this child I'll need to dupe to so that it goes into this other file. So that'll be open that file up, open it for writing, in this case open it for reading, and then do some dupe to manipulate the file descriptor table so that output goes in there. Again, we've got some labs that cover those specific topics expressly to set you up to succeed on this part. So go back to those if you need some insight as to how to handle this part. The parent process then is responsible then for, after forking off the child, waiting around until it's finished before proceeding. And this is a fairly straightforward, call wait in some version, wait or wait PID. Importantly, you'll have to get the child's status out to check on it, because the standard convention in a build process is that if there's a syntax error in hello.c, then this target can't be updated. GCC will bail out, which means the whole build process terminates. So GCC will return an exit code in that case that's non-zero, and it'll be the parent responsibility of Bake to say, oh, this child that I forked in exec, it wasn't successful. So I'm going to return up the build process that I can't make hello.o. So I'm going to terminate trying to build hello, and I'm going to terminate like this demo thing over here. In that case, then it sort of unwinds the whole recursion down that way. So it'll be important then to capture the status of what that child process is like, and as well handle certain situations like, oh, the child process might not be able to set up output directions, like because someone gave it some bad file or said redirect your output into a directory or something, and you can't write the directories up there. Or it might be that someone plopped in, they misspelled a command, they just write GC instead of GCC. And so on execing, this actually fails because no image for a program called GC can be found. And so the child should report certain kinds of errors of that, and the parent can pick it up and sort of reiterate that. So numerous failures there, and it's basically an exercise in sort of assessing, like, okay, is this successful? That's fine. If it failed, why did it fail? There are a bunch of reasons for that. Okay, I think that's enough there, and sort of some descriptions of different kinds of failures and the actions to take on it. Problems 3 and 4. Oh shoot! I see I didn't plop down my diagram here. So I'm going to pause for just a second to get that up because it's probably also not online. So, but I want to make sure that's the case. So, give you just a second, Yang. Okay, that just took a second because I needed to find the file and change the timestamp so it actually got pushed out here. A quick word on the structure. It's tempting to think of Makefiles and Bakefiles as they'd appear in sort of textual form as just, a text thing. But what they're really encoding is a set of dependencies that forms a sort of data structure. Formally, this is a directed acyclic graph with a link to Wikipedia here if you want to go read about it. This is fairly similar to a tree, except that it's not quite as regular as a tree. A short picture of a really simple one here demonstrates this. For instance, a standard structure of a program might depend on a couple different sort of source files over here. Those source files, they depend on object files. Object files depend on some source files, but as well may share things like, they both depend on some header file that encodes things. So, for instance, every file in the Bake system sort of depends on that bake.h header file. So a tree, this is different from a tree in that, like, I couldn't have sort of cross links like this. But rather than this dependency is like just a little bit sort of less regular there. You get more complex versions of this where like higher up dependencies depend on lower down things, so that's there. But generally, the directed acyclic graph part of this is that it's comprised of nodes, or more formally vertices, that's the little round things in here, and edges or arrows between them. The arrows have directions. So the vertices and edges, that's a graph. The directionality, that's the directed part of it. And the acyclic part means that no dependency lower down should ever sort of depend on something that's higher up, which could potentially create a cycle, which is not possible then to perform an effective build on, because you're going in circles. Before I do this, I need to do this. Before I do this and this, and then I go back and chase my own tail there. So the checking for dependency cycles like that will be part of one of the makeup credit problems. We won't worry about it now. For now, you can just think of this sort of as tree-like, with the caveat that multiple parents may sort of point to an individual child here. And maybe that's more indicative of an actual family tree or something like that, where you can have like different sets of parents with different generations along there. But no matter there. All right, so in that sense, this problem deals with two functions that are central to walking this data structure and performing certain activities that are relevant to the bake system. For example, one might want to know, should I update this hello world program? If it exists, then the answer might be like, no, I don't. Except that if someone made a source file change to foo.c, then the source code is actually newer, might have bug fixes in it that aren't reflected in the executable hello world program. So the first function, bake set updates, is designed to recursively walk this data structure and determine each thing in here, does it need to be updated? And that will be a combination of properties about the thing itself, as well as do any of my dependencies need an update? So hello world might exist and look just fine. It's just that if you work your way down and see, ooh, this foo.c is actually really new, like it was updated just a few seconds ago, and this program was compiled minutes ago. The .o file as well was compiled minutes ago. And so this foo.o needs to be updated by recompiling foo.c to create it. And the foo.o then needs to be relinked with other things to create a fresh copy of hello world that finally reflects the changes that were made in the source file. If the header file changes to say, oh, some of the interfaces have changed things, then everything needs to be rebuilt. On the other hand, if you look and say, oh, hello world was, it was built a minute ago. The last time someone updated the .o was 2 minutes ago, and the last time someone changed the foo.c was 3 minutes ago, then everything's in sync. It's like, oh, this is actually older than the program, so it reflects all of the changes that were down here, and likewise for everything else, in which case I don't need to rebuild anything here. So bake set updates, its intent in the world is to walk through this thing and determine if any of these need to be updated, then certainly this one does. If they don't, then maybe this thing doesn't need to be updated. On the other hand, you might say, hey, update hello world, and find that, oh, it doesn't actually exist. So certainly its commands need to be rebuilt so that this file, which doesn't exist, can be created. And then maybe we can worry about updating it later or not. But if it doesn't exist, it certainly needs an update at that point. Each of these nodes then in the DAG then has a bit that marks it. It's the update bit, or properly rule update bit, I think. And that marks it as in need of an update with a 1 or 0, not in need of an update. Basically, true, false out there. And the point of bake set updates is to undergo some complex machinery to visit each of these and mark them as needs update, doesn't need update, needs update, etc. So there's some specifics to this, but it is a recursive function. And so you start someplace, but before doing much with hello world, you would visit each of the dependencies to say, do you need updates? The recursive nature of the function will return 1 to say, yes, it needs an update, or something, this needs an update. Or as you'd call on a dependency to say, no, doesn't need an update, return a 0. Yes, needs an update, returns a 1. And that dictates, yes, I need an update as well. Even if none of the dependencies need an update, there may be a reason that hello world would need to be updated. For instance, like I mentioned before, an absence of the fact that that file is there. The pseudocode that's given here should give you an idea of the general structure of this function, and draw your attention to a few special cases. For instance, over here, the bake recursive func would make use of your function to say, hey, I'm looking at this target, fish out the rule associated with it. If it can't be found, well, then someone screwed up. They've asked to update something that there's no rule to update it, so bail at that point. But after some initial checks, essentially loop over the dependencies, recursing on them using bake recursive func, and then capture return values from them and return them. That structure is good both for the first function up here, bake set updates, as well as bake do updates. So the update business here is discussed in more detail down here, but this is the general structure you'd expect, with details and vagaries to be filled in for what does it mean to perform some initial checks or actions. Well, that depends on whether you're setting the update bit or actually doing the commands to update the function over here. But both of them will follow a similar structure to this, so expect that. There are numerous other things to account for there. For instance, the update flags, some error messages associated with different things, and some special cases like, oh, if this function or this rule clean, like it has no dependencies and it has some commands to run, then you should always update this. As in, anytime I type make clean, I'd want this command to be run. On the other hand, if it's has some dependencies but no rules, then some slightly different special cases associated with that. You'll have to, at various times, check for the presence or absence of files while determining is an update needed. And that's most efficiently done with the access system call. Recent lab dealt with making use of that to check if a file exists or not, and bail if it doesn't. Or in this case, it would be if it does exist, then go on to check some modification times. Again, useful by using stat. We'll want to get somewhat high resolution timestamps, and so modern versions of struct, particularly on Linux, have two fields that encode the modification time, the STM time that comes out of the struct, as well as the STMTIM. You notice the very subtle naming difference there. The first is just a single number, usually a long, possibly an unsigned long. It's just that should be signed so you can represent time differences. Sorry. But this only gives you second resolution. So if I change these three files, like it's like GCC this one, GCC this one, GCC this one, and each compilation only takes less than a second, then each of them will be marked with the same timestamp, 123, or it's like 122 and 30 seconds here. When in reality, there was like a half second or a quarter second difference between them, which would be reflected in this more high resolution time over here. STTIM has a couple fields, including a nanosecond, or not nanosecond timestamp there. So in that respect, it's good to make use of this one. I think Grace, the idiotic system that it is, only has second time resolution even with this thing. But make use of the time spec thing here along with this provided function to get a difference between those times. And all should be well for that. It's similar in spirit, this one, to a strcomp that'll tell you, this time spec A versus time spec B, this one is less than or greater than or equal to this other one by returning a negative, zero, or positive number. Finally, then, the performing updates part, which is the subject of the second function here, actually bake do updates. You'll want to execute commands. And so you'll definitely make use of the function that you had written previously, that bake execute command, the last function that you wrote in problem 2 over here. That will fork off a child process, exec it, and so forth back here. This will be done repeatedly for each of the commands, checking that, if they succeed, then go on to the next command. If they fail, then cancel the whole sort of do updates recursive business. There are a bunch of output constraints here. It's like, you're supposed to print out some certain things. And this is just sort of give an idea visually of where you're at in that tree. So as you would update this kind of a DAG, it'd start up like, I need to update hello world. And previously I determined it needs an update, but before I do that, I need to update this one. It doesn't need an update, so I will immediately return back here, and before I can update it, I'd recurse down of this other dependency, bar.o. That needs an update, and so I'll recurse further down, find that I don't need to do anything to this, but then I'll issue a command like, I've got to update this with a gcc-c bar.c, and that sort of output constraint here gives that better idea than what's done before what, to make sure that in testing you are executing and visiting these dependencies in the proper order and doing things that on the dependencies before the actual target there. So some output terminology here of like, substitute the command you're actually working on and how many are the target you're actually updating and the number of commands that are associated with it there. So there's, I think, a lot of value in looking at an example here. Here, as you would do a bake on this primitive little bake file, which I think is one of the test cases, then you'd see output that looks like the following. We'll presume in this case that everything needs updating. And so the initial bake, it is invoked over here. the first thing that's detected is that there is no x.o. So the default call is all, which means I'm going to build both of these two things starting with prog1. It depends on x.o to get down to x.o. Maybe visit this implicit rule for x.c and find, yeah, the file is there, but there is no x.o, so it needs to be updated. So that's the first thing that's updated by issuing a gcc-c. That's a fork wait. Once that's done, then visit the second dependency x.o here, or see y.o, and similarly compile that thing over there. And there's one subtlety to this that I want to point out because I imagine folks will forget it at some point. If you count the rules here, 1, 2, 3, 4, 5, 6, there are 6 of them. And you'll note when this bake completes, there will have been 6 updates performed, one for each of the rules that are over here. Now, if you're a little bit sloppy with this, you might find that, oh, like as I update program 1 and program 2, program 1 requires me to compile x.o and y.o, and program 2 will require me to compile x.o and z.o over here. There's a duplication here of x.o here and x.o here. A properly built makefile or make system and bake in this case should identify, oh, there are 2 different things that depend on this x.o, but I only need to compile it once. And that's why you'll only see the x.c compilation a single time over here. That's most easily facilitated by saying, when I initially go through with set bake updates, I might set a bunch of bits to say these things need to be updated. But as you visit them in the bake do updates, which actually execs commands to update rules, when something is updated, you'll clear that bit, that update bit. And that ensures that if you ever in a bake do updates land on that node again, and you'll see, oh, it doesn't need an update, like we skip it and back up in the recursion. And that's how you'll achieve this kind of a behavior where the things only get updated once over here. So I have some more dialogue on that down here, but no worries, as well as some of the output over here, including one little nugget that you'll need to, on an error, print out the file and line number that the error came from. So this would be like, oh, some GCC fails right here because you had a syntax error and something. You'll need a line number and file where that comes from. Keep in mind that these are bake functions, so you'll at some point be working on a command and have access to bake t. And if you look at the structs for this, the bake t itself has a file number. And in the parsing, each command, as it's read in, it notes the line number that it was on. So this makes it relatively easy to say if this GCC failed due to a syntax error, it was at this line in this bake file that you were on. Okay, the last part of this then, after walking through that, is just a little bit of post-processing where you're responsible for going through, taking all of those bake commands and in their raw form, sort of modifying them. So this will be to say, oh, the initial sort of versions of things, they might look like a token array of cat, dep1.c, dep2.c, a symbol that means output redirection, and deps.c. And your objective here in this post-processing is to take this raw thing, which contains the output redirection symbol in that, and modify it a little bit. To take the command, detect that this is present, and set the out redirect bits, populates the output redirection sort of file name with this thing, and then remove these things from this, because if you handed this to an exec, it would fall down and not work properly there. So afterwards, you want the things to look like the following, like where the little output redirection is removed and the deps.c, that's removed as well. What remains is what came before it over here. And then certain fields like the flags and the output redirection, those will be set appropriately. There's one case, each of these for silencing, for input redirection, etc., as well as, in some cases, you don't make any of there. Now, this should happen then in the context of this bake post process, as in just run this function, post process command on each. The design here is such that you might later on, if you're expanding this system, fill in some other things for post-processing, like, oh, if you added variables, you could add expansion of those variables in the sort of raw input in at this stage. But basically, this is just sort of a small function to sort of those things, so that then you can make use of it in a main function. This is the last part that I will mention, as this video has gone on way too long already, but for complex things, some complex explanations is required. The main function is where you'll tie everything together and see, oh, this is how the pieces fit together overall. The first thing you'll want to address is that the bake system requires an input file, that it can't be run just sort of without stuff. But an invocation like bake will use a default name. Look for just Bakefile in the present directory. And that's similar to the convention of make. You can just type make, and it will assume you didn't give me anything else, so I'm going to look around for something called capital Makefile. Just like make, though, you can feed in a different file. So with -f, you can specify, I don't want the default makefile or bakefile. I want bakefile2 or this other thing, dune file or makefile or something like that. As well, then, the command line options allow you to specify a target. So make test, make all, make zip, etc. So these could come in a variety of shapes, either the target as the only thing or the target as the last thing on the command line, with optionally this -f in between them. We won't, because command line processing is a pain in the butt, support alternate orderings like, oh, this target with over here, this bake file. So you don't have to worry about that part. They'll simplify the command line handling just a little bit, because you can see 0 arguments, 1 argument, 2 arguments, and 3 arguments. So that makes for a nice if-else case there if you're looking around. The logic for main maybe needs just a little bit of a treatment. So we provided a somewhat lengthy pseudocode for this, but you can read into these things an overall structure of do some command line processing, then read in the given bake file using that bake create from files provided function, call your functions to post-process, add implicit rules, etc. And then poke around to figure out if there was a command line target or a target given on the command line, set that. Otherwise, go into the bake t struct and fish out the 0th rule, because its target is the implied one. Again, if you have a bake file that looks like this and someone just says bake, then this demo here, that is the default target, so the 0th one to appear in the file. That's it there. Then make use of your update functions. So do an analysis to determine does anything need to be updated. So that'd be set update. And if it does, then do update. Various errors can occur along this way. And so as you would detect those, you want to make sure to print out an appropriate error message and free any memory before exiting with a failure. There's some notes on that down here. That C has 2 ways to exit, indicating a sort of default failure. I mean, the slightly sloppy way is like, from main you return 2 or 5 or something like that. But there's also a symbolic exit failure here. You can return that if you're in main or from any place, exit with that, and that will prematurely exit the program with the indicated exit code. There's also an exit success if you like, but I usually just return 0 or exit 0 in those cases. And as well, then, as you detect errors along the way here, there are some appropriate messages to be printed down here for it. Okay, that's, I think, my overview. This is a modestly complex program, but if you finish it, or even if you don't, you assume some parts of it, recognize the fact that, hey, you're building something that is actually a real and useful tool. And when you're finished with it, you can essentially build bake using bake. You might have to rewrite the make file a little bit to make it a little bit easier there. But this is then something that actually approximates a real tool. And real tools, as you'd want them to be useful, inherently have some complexity to them that makes them harder to build. But you only really get to the point of being able to build real things if you sort of work on versions of them like this. And so if this is a bit of a struggle, fear not. That'll pay its dividends in the long term in terms of gaining experience in debugging and so forth. The last thing I want to draw attention to here is that there are various manual inspection criteria. Some of these are more or less alluded to in the discussions of each of the problems there, but it's, as always, a good idea to look through these things. Generally, it's about 10 points a pop for each of the problems in terms of the raw sort of, if you wrote this function and did a reasonably good job, we'll look for some things in it, maybe dock you a couple points, but otherwise give you full credit. But each of the problems as well has some style criteria associated with it. It's mostly the same stuff around here, but each of the problems has individual style of code. So if you poop out and stop writing comments by problem 4, then you might get dinged a little bit out there for it. So bear those things in mind, and as you finish up, maybe review them so that you're not, or look ahead, because some of them contain hints about, they utilize these 2 system calls for various things that are of use. Okay, that's it. Submit to Gradescope as always, and later today I'll have that submission criteria for you, as well as hopefully, possibly, as well the makeup credit here. Happy hacking to you, and enjoy the bake-off.